assumptions are reasonable. So, first thing that we test for is actually the linearity assumption, and then we test for the independence assumption, and then homoscedasticity, and then normality, and then multi-collinearity. So we learned what these assumptions mean, and if we don't test, then what would happen to our results, right? So each and every step is important, and I do have an example. So basically, like I got it right here. So what we do here is we have several steps. So we actually also fitting a multiple linear regression model. But before you fit the model, you need a fabricated data set. So we said we do have a data set that contains 5,000 records, and that contains, let's say, ID, age, gender, substance use, like typical things that we had earlier, data. And first thing is, we write the model, the multiple linear regression model. So as we discussed earlier, so instead of having one dependent variable, we have multiple dependent variables. So the summary of the model, if we test, and then if you get the summary of the model, if we test for the model fit, we would be able to see if the model fits well with the data. In addition, so we need to definitely test for the linearity and independence, homoscedasticity, normality, and then finally for multicollinearity. So all these steps are necessary before you do this. So basically, like, this is okay to have it here, but ideally you have to do it in the end after all these things are done. So I mean, it's okay to test it here also, but before you use the model, definitely use the results. Definitely you need to test for all these things. Okay, so let's see how it works. So we are using these libraries. So you may need to install the libraries that you don't have. So ggplot, definitely you need to plot. And then some of these tests and functions that we use here are coming under these libraries, okay? So as you can see, these packages or libraries, I use interchangeably those words because it's the same thing. And they are coming under these packages or libraries. So you make sure, so you install these libraries. So I think if you remember the installation, the command that you need, the function that you need to run, cars, and then you also have to, so you install it, and then install cars, and then you install mass, and then you install stats, and you also have to install ggplot. But I used this earlier, so I know you installed this library earlier, so you may not need to do it now. So, but other ones you will have to install before you run this code. Okay, so but let's go over what we have here. So these things yesterday we talked about, how to create a data set, like kind of fabricated data set. So again, this is not a real world data set. So just for your learning purposes. So it's okay to have something like this. And so we do have the data set right here now. And yeah, so we are going to test model. So basically we are focusing on substance use and then see how other variables impact substance use. So in that case, substance use would be the dependent variable, while others are independent variables. So that's what we have here. So substance use, age, health score, sleep hours, work hours per week. So you can see all these things are continuous variables, right? So we don't have categorical variables at this point for the simplicity. So we'll learn other. So you will learn other regression models down the road, but right now we are just focusing on the most fundamental multiple linear regression model, which includes continuous variables, the simplest way. And then we also have to assign the data set into the function, LM function. And then we will see what the summary says. And this is the summary. So immediately, like, I know this is something eye-catching, right? I mean, what's the p-value? I mean, that's like every researcher will, like, immediately look into the p-value. Is it significant? And, am I good to go with my research hypothesis? Like, yes, it's good to take a look at your p-value, but, we also need to know what's happening behind the scene. And immediately, when we type this equation, so we are actually going under lots of assumptions. So just because you have these fancy, like, good looking p-values does not mean that you have an accurate model with valid results. So that is why we are not gonna read these p-values and then be happy with it without testing any of these things, okay? So first thing of these, the test of the assumptions is gonna be the linearity. So we plot residuals. So basically, residuals are like the errors, right? So we will test if they are going to be fitted. So with the model. So what we do here is, we remember in ggplot, we have to assign the data, and then we have to give the aesthetics, right? What x is being, like, included, and y, and what's the y, right? So we have to know what values we should use for x and y coordinates, aesthetics, right? So we learn about this geometric plot, ggplot last week. So anybody who do not understand this, please go back to that recorded session and learn. And then and then we fit it, and then we will see what it shows us. So let's try to plot and then see what the plot says. So this is how the plot looks like, right? So if you go back to our notes, so we need to test what do we have to look for, how to check linearity. So create a scatter plot of residuals versus predicted values. So residuals, like, we have them in y-axis, right? So residuals, you can see residuals are in the y-axis. Let me make it a little bigger. Right here, so you can see residuals are in y-axis. And then in the x-axis, you have the fitted values. Those are the outcomes from the model, right? So they should not have any relationship. So look for a random distribution of residuals without a discernible pattern. So that is exactly what we see here. So if you see some sort of a pattern, so for example, let's say like when featured values increase, the residuals also increase. So that is an indication that we have a problem with the model, right? So that means we have significant things that we have omitted in our model that we excluded, that we cannot simulate. So there's some things happening behind the scene, and so we cannot say this linearity can be assumed. So that is the thing that we can say from this check. And then we can also look at this, and then you can see basically if they have any significant um, uh, differences between the residuals and the fitted values. So for example, the scatteredness, like if they're too close to each other, so then and then you may need to see if the data is really homogeneous or heterogeneous, so because these results, the residuals and fitted values also would indicate some sort of a noise in the data. So you can look at this and understand a few different things like I explained, but mainly we are going to check for the linearity using this plot. And this function is being used to check for independence. So this Durbin-Watson test. So let's see what it's going to show us. So so the Durbin-Watson test, we are getting a autocorrelation with a p-value of 0.37. So if the p-value, so let's see what we have to test here. Use the Durbin-Watson test to detect autocorrelation in the residuals. A value close to 2 indicates that residuals are independent. So we do have an autocorrelation, and there's lag 1, so which is not being considered as an autocorrelation, and we also have a p-value of 0.37. So we ideally do not have any autocorrelation here. So because so autocorrelation is a thing mainly that we find in temporal data. It's like what it's actually a big concern in temporal time series data. So, but in our case, we don't have to worry about that. And the next thing that we are going to test for is the homozydicity. So homozydicity, we plot the residuals against the predicted values. And then it's pretty much the same plot that we have here. And they look for a constant spread of residuals across all levels of predicted values. So let's plot. You can see it's pretty much the same thing, right? So except that the title is different. Yeah, so this is how we test for homozydicity. So if you see, like, what does this mean? Homozydicity refers to the condition where the variance of the residuals is constant across all levels of the independent variables. If this assumption is violated, it can lead to inefficient estimates and affect hypothesis testing. So what it means, like when the fitted values increase, the residuals should not increase or decrease. So otherwise, it's called heterozygosity. So as long as it stays as like flat in horizontally. So when the fitted values increase, the residuals, if they don't show any visible patterns of changing, which is actually the case here, we don't see any pattern. So it's pretty quite random, and we don't see anything that's increasing. or decreasing with fitted values, right? With increasing fitted values. Okay, so that's also good. And then we check this QQ plot, quantile plot. So so here we test for normality. So let's go back to our slides and see what normality is. So the normality assumption means that the residues of the model should be normally distributed. So this assumption is particularly important for small sample sizes, which is actually our case, and hypothesis testing. That's what we are doing here, right? So, so what does it say? So actually, so before we get to this normality, why don't we try to execute whatever we have up to this point? So before we get into all these things, so can we try in your environment? I can give you a few minutes to try to install any needed packages to execute all these lines. And these are the packages that you need. So you need to change the name of the package, or else you have multiple, of this. You can just copy and paste, and then you can add all these things. And ggplot also, like this. Install them if you don't have them, and then load them. So you also have to load it. If you just because you are done with the installation would not necessarily show make it available for you. Okay, so you have to load the library package into your environment, current environment, your project environment using this command, and then you get the fabricated dataset loaded, and then run the model and come all the way up to step 5, okay, before we proceed. So I'm going to give you like a few minutes to make sure that you can do this. Again, if you want to do like a good, thorough research, I really would like you to learn this. So do it right? Or don't do it, right? So that's my philosophy. Let me, okay, I may have to give you the code, right? So I think the first part is not available. So the entire, actually, I cannot copy the whole thing because it exceeds the limit. Okay, so let me just copy paste the first 30 lines. Okay, that is also too much. Okay. Okay, so you should have these things. Actually, I don't have all these things in my slides. Okay, so but I'm giving you them right now. Okay, so in the chat, there is a question, what is, hold on, I didn't see that earlier clearly. What does the red colored line show us? So that is this, the zero. See, like it's the y-intercept, residuals are zero. So that's like the reference, right? So if the residuals, at this point, if the residuals are zero, so that means like there's no like zero error line, right? So that's the reference line. Okay, so if you look at this like geometric H line, it's actually GEOM underscore H line. It's actually drawing a horizontal line at y-intercept. See, y-intercept equals zero. So it's just showing the reference. Okay, so I hope you managed to do that and all the lines. And let me know if you're having any difficulties. Okay, so let's move on to the next part. So QQ plot, right? So what is this QQ plot? So let's go back to our slides and see normality. So we are testing for normality here. So what is normality? Like normally distributed, right? So there's, so as we discussed earlier, all these variables are continuous variables, right? In real world, if you observe continuous variables, so we assume they get this like, normal distribution because, the natural things that we observe, the things that happen in, in real world, we assume, that it follows a normal distribution. But is it reasonable to assume that way for all these variables, right, that we consider here? So we don't know. So that's why we need to test. Okay, you can simply say, yeah, under this assumption, this is true, but is your assumption true? Can you rely on that? So that's what we are testing here. And so, so this assumption means that the residuals of the model should be normally distributed. So we are testing for the errors, the residuals of the model, and they should be normally distributed. And this QQ plot is what we are going to use. What is this QQ plot? Which is actually the quantile plot. So this is a graphical tool we use to compare two probability distributions by plotting their quantiles against each other. So when you're using a QQ plot to assess normality, in your residuals, so one axis is going to show you the quantiles of a theoretical normal distribution, and then the other axis is going to show you the quantiles of your sample data. So what are these quantiles? I mean, we also talk about quartiles and quantiles, right? So you need to know what these things are. Actually, quartiles are actually a subset of quantiles. Okay, so quartiles are, we are actually getting like 25%, 50%, 75%. That's 4, right? 4 divisions when we talk about quartiles. So um, quantiles, it could be any. So it could usually like 50%, 50% quantiles. So we just divide the data into these these percentages, right? So we say that the 25th percentile, 50th percentile, 75th percentile. So these are like, we just divide them into like, equal parts, right? So based on the median. So if you say like, if you just divide it at 50%, it is just based on the median, okay? So we basically divide the probability distribution into intervals with equal probabilities, okay? So it's just like, if you put it in a simple way, so usually a quantile point is a point that divides the data set into continuous intervals in a specific proportion. So probabilities are basically proportions, right? So that's what we measure. So let's look at our plot. We'll run it. It's this one. See, we are using QQ-plot function, right? And then we have to give the model, our model that we tested. So the linear, multiple linear regression model, and then main function, we have to identify what kind of a plot it is. So it's a QQ plot, argument. So if you go to help, you will see that there might be some other arguments that you can include that would add some other parameters. There we go. Okay. So now, as I explained before, so we have this plot. So what does it say, right? So so we can say, it's aligning with the diagonal line, right? So majority of the points. So you can see all these points, right? So they're actually line, along the diagonal line, right? So this indicates that the residuals are approximately normally distributed, which is actually a good sign for the normality assumption. Deviations of the extremes, but we also see some anomalies, right? So some deviations are there at extreme levels. For example, if you look at, that's my annotation. Okay. These areas, right? These areas. So you can also see that there's some deviations, right? Both ends, right? So this tells us that the residuals at the extreme values are not perfectly normal. Okay, so that basically, like, these are also called like some sort of outliers in your data. So these outliers could be really problematic, in some cases. So there are ways to detect outliers in your data. So before we get into this, I don't think if I discuss that concept much, but that's also another thing that people usually do. Like, there's lots of tools that we can use to determine, outliers in the data, like Mahalanobis distance and different kinds of distances that you can compute and then determine the outliers. Okay, so what can you do about these things? It could not be a serious issue because they don't represent a huge proportion of your data, right? It's just maybe like 10 out of 5,000 records, right? So that may not be a huge problem, but if you want to be like more precise, if you want to do it even like, in a better way, so you can take care of these outliers as well. So you can say these kind of plots are really also very informative. So you can make really informative decisions based on these plots. Okay, it's not just going to tell us, if they're normal or not. We can also identify some other patterns, characteristics in your data. Okay. Yeah, so the last step is is testing for multicollinearity. So let's go back and see what that is. Okay, so what slide it is? It's right here. Okay. So here, we test for multicollinearity. So this occurs when two or more predictor variables in the model are highly correlated with each other, which is not good for us, right? Because if they're correlated, so that means, they are not independent, right? So they have some sort of a dependency. It could be coming from another external variable completely that we have not observed, right? So maybe that outside the external variable is impacting this variable, right? So for example, if you go back to a model, so let me explain this concept. These things are really important as researchers. We need to know what's happening. So,
Dr. Gustina,
yes.
sorry for interrupting. There's a request to share the syntax for 6 and 7. So I think that's the QQ plot.
Oh, yeah, I'm sorry. I forgot. Yes.
Thank you.
Okay, welcome. Okay, so yes, you should have it now. Okay. Okay, so so I was talking about this, right? So if you go back to a model, so right here, right? So if you pay close attention to this, so substance use score, right? So what does this say? So we are saying a story here. So what is the story? We are going to say, the substance use score is going to depend on age, health score, sleep hours, work hours per week, right? So is this the true story? We don't know, right? I mean, we are just telling this based on what we find in our data, right? So the data can tell many stories. So that's what we are trying to reveal through these models, right? So, but we also need to know that, this data is not perfect. We also may not have everything that we need to determine the substance use score, what affects the substance use score. So here we can see let's say 1, 2, 3, 4, we have 12 variables, right? So maybe there's another variable that we didn't even think, and so we didn't observe it, right? So we did not record it, and we did not collect that data. So for example, let's say income, and our income is here, right? So for example, let's say something else that we don't have here. So I don't know, something, let's say the neighborhood characteristics, something like that, right? So that we have not included, right? Or let's say parental influence, so that we have not considered here, right? So maybe a depression index or something, right? So we don't have it, right? So, but maybe the depression in index, for example, let's say it can impact, both health score and sleep hours, right? So because, the depression, maybe it is causing some sort of, health problems, and also it impacts sleep hours. So since the depression is something that we have not observed here, right? So and it is impacting both health score and sleep hours. So you may see a relationship between health score and sleep hours, so which could cause multicollinearity. It could also be related directly health score and sleep hours. So we don't know exactly. We have sometimes if we feel like we just fly blind here, with these models. If we try to dig deeper, are we really doing the right thing? We are just doing our best, right? That's all we can do based on what we have. It's not like we have to stop what we are doing just because we don't have a really perfect comprehensive data set. We just write down limitations. So these are the limitations. We need to be really honest and clear about our model. So this clearly we have to state, these are the assumptions that we made. we don't have a holistic understanding. So those things are really important. Like, what is holistic understanding? It's like, so we need to know the the system, like, as a whole. Like, this is substance use score is dependent on many other things that we have not observed. Maybe the most important thing is missing here. We don't know, right? So that's why we cannot give solid, straightforward answers to anything. It's so that's why. So we always say, all models are wrong, but some are useful. So it's coming from a British statistician. I forgot his name. So that's actually true. Any model that we develop is wrong, but some are useful. They could be useful because even under certain assumptions, product limitations, they can still be informative. They could be helpful for us to make decisions and understand how things happen. Okay, so, but as far as we know, to the best of our ability, we have to explain what the limitations are. We should never hide, because this could be misleading, and somebody could, like, use these results and do something that could not be a favorable outcome, right? So as good researchers, these are really important. Okay, so so most of these tests can actually tell us, well, if we are doing things right or not. But still, it's incomplete because we can never observe everything that we need to model something, right? That's nearly impossible. So I just wanted to explain those things to you. Okay. All right. So I ran this and then and see what this gives us. So what is this VIF actually? So it's better to know at least what it is, right? So yeah, I'm not going to teach you all the concepts because we don't have a lot of time to do all that. But VIF stands for variance inflation factor. So it is a measure that we use to detect the presence of multicollinearity in a regression model. So what do we really measure here? So so VIF actually quantifies how much the variance of a regression coefficient is inflated due to multicollinearity with other predictors. So if there's multicollinearity, it's going to be inflated. So that's what we are going to measure here. So for a given predictor, a higher VIF actually indicates that the predictor is highly correlated with one or more of the other predictors in the model. Okay. So, but what is an acceptable value? Like usually VIF, like it's like 1. This indicates no multicollinearity. Okay, so that means the predictor is not correlated with any other predictors. That's what we see here, right? So which is good. So we are good to go. But if the VIF value is between 1 and 5, it suggests that there's moderate multicollinearity. So which is also generally acceptable in many research domains. But if VIF is greater than 5, that indicates a significant multicollinearity. So definitely that could trigger further investigation. Okay, so we got to be careful with that. So so we like I said before, since the VIF values are all around 1 in our case, and this fabricated data set, you can be confident that each predictor variable is not highly correlated with others. So this means that the regression coefficients are reliable and not inflated due to multicollinearity. All right, so it's all good. And now we can talk about the model because we can guarantee that the model, the assumptions that we made to get these results are reasonable, right? So yeah, so we talked about these things. I'm not going to explain all these things. So how to define. So you can see some things are important here to definitely pay attention. So you need to report So you also need to learn what needs to be reported, right? So when you present something to an audience or in a paper, so you have to make sure there are certain things that you need to report, right? Okay, so we are good with the model, and I explained all these things. I'm not gonna spend more time here. Now let's go back to um, the notes, and yeah, so we did this. Yeah, keep these notes safe, because in the future, if you are planning to do any of your publications, this could be helpful for you to do a better job. So I'm not criticizing anyone's work, but a lot of people don't know, they're not aware of all these things. So unfortunately, like there are lots of misinformation even in published articles, because they are lacking some of this knowledge. So yeah, so we did all these things, and we learned how to interpret the results. So there is an activity for multiple linear regression. So which is something we just did that actually, right? So through that model, so when we test for those assumptions, we already did one, but we can repeat it. We can redo one model and try to see what it gives us. So let me clear. Okay. So you just have to actually copy paste. I have made things easy, but when we get to the activity, which is something that we are going to do soon, we are not copy pasting. You're going to like work with me and write your own code, okay? Which is important, because we cannot always copy paste. So we have to write our own program, right? So we need to know how to do that. So you can actually do this with me, okay? So let's because since I have already explained these things, there's nothing else to explain. We just want to run this and see the results. That's it. Okay, so this is it. So again, I think it's pretty much the same thing that we ran earlier. So I don't know if I have anything different. So because this is the code that I had earlier, so I just prepared another one. Actually, the sample size is a little bit larger, so you can see if things change when the sample size increases, right? That's one thing that you can learn from here. So earlier we only had 5,000, but this time we have like 20,000, right? So you can see if the model fit improves, and you also have to test for any of those assumptions, right? So all those 5 assumptions that we made, right? Sorry, I missed these commas here. Okay. Okay. So if you run the model, now we can see. So when you add more records, you can now you see, we don't have any significant results, right? Earlier we had some, but we don't have any now. So yeah, so that could be the case, right? So when you increase the population size, some of these effects could be insignificant, right? So that we are we are using in our hypothesis. I'm going to give you a few minutes so you can run it and then try to see the results. Okay, make sure you can do this by yourself.
Dr. Kusgola,
Yeah.
just for clarification, so you want them to run the model and then the for test?
Yeah, so I just want them to run the model. They can also test for those things that we did earlier. So like multi-collinearity on that, all of that can be like tested if you are interested. In that case, I can give you a few more minutes. I mean, I don't know. I mean, I think we are almost done with this part. So the next thing is actually, no, we are not done. So we have to learn about the forward and backward elimination. Yes, so we got a few more things to do. Yeah, so if you can just run this, that would be enough. But definitely at leisure, I really want you to practice all these things. So for this model also, as an assignment, for you, test for all those 5 things, okay? Linearity, normality, and all those homoscedasticity, everything that we discussed earlier. So, and then you can change the model, right? So for example, let's say like you remove health score, and that's what we are going to do later, right? We haven't, that's the next step, right? So we just have all these variables right now, but we don't know if we need all of them, right? So we will do that forward and then backward methods of performing this analysis. Okay, all right. So I'm assuming you had enough time. Okay, let's see what these things are. I think we talked about this earlier. So this forward selection and then the backward elimination. So so what we do here is like, forward selection. I'm sorry, I touched the microphone. Forward selection includes, adding the, the, the independent variables one at a time. So we start with the basic model where we have no independent variable at all. So you can see just like substance use score. We are just testing, if it's just having substance use score itself, what happened if it actually changes without having any dependent or independent variable, right? So if it changes that way, so maybe there's some issue with our data. That means we may not have everything that we need to determine this score, right? So that's the first model. And then we add more and more. So how do we do that? We have this step forward model, step AIC. So there's a function that actually automatically does that for us. So, but ideally, you have to add one at a time. So for example, let me just show you this. Okay, so let's get rid of this part because we don't need that right now. So, but we are copy pasting this and we are using this mass function, sorry, mass library, where, they have developed this step AIC function to make our life easier. So then what this function does is like, it iteratively adds one by one all these variables. See, we give the score and then see the model fit, right? So based on AIC and BIC. So I don't think if I'm going to spend time explaining what this AIC and BIC, they actually fit indices that we use to determine model fit, okay? But definitely you can research on that and understand what those concepts are. Okay, I don't actually have time to go through all those things. It's basically learning about these things actually takes about one full semester. So if you want to learn everything about model fit, okay, it's broad, but just by knowing what these things are and how to use them in your model, that's fairly enough. Okay. So ideally, like I said earlier, so you make sure you have the library loaded. When the library is loaded, so we define the basic model, right, for the forward selection. So the basic model, so again, we are using LM function. So the independent variable is substance use and independent variables are none. So we have nothing, right? If you run this model, so you would see, yes, it's gonna show you. So let's summarize. Summary. Summarize us. Right. So it's talking about the intercept, right? So intercept estimate is 50 and p-value is highly significant. So it looks like it's a line, right? So if you just plot substance use score, and then we add one at a time, right? So let's say level 1, right? So level 1 model or step 1, however you want to call it. And I'm just gonna add age, okay? Just age. So now we can see we are adding them one at a time. And now let's run this. And then we also get a summary. So age seems to be not statistically significant. And then you add one more models, like, parameters like this, okay? The independent parameters. So step 2 model, we are adding, let's say, age plus gender, okay? Gender is a binary variable, right? So maybe we should not include that. Okay, let's take that off. In our case, gender is a binary variable. Health score, sleep hours, work hours, that's fine, but let's not have binary variables here, okay? Health score. Okay. And then you get the summary. And you can see that's also not significant. So you should be able to see the fit. So since we are not measuring that, the AIC or BIC value, you are not going to see that. But the good thing is, this function, so it's actually doing this, what we are doing right now manually. We don't have to write all these things. This like just one simple function, which includes all these things in addition to computing the AIC and BIC values, AIC values. And then iteratively, it will add all these things and give us the the best fitting model. Okay. So that's what we are going to do. Instead of doing all these steps, it will automatically add one independent variable at a time, and then it will run. Let's see what it's going to give us. Okay. And then, yeah, it ran. Right. So it's also giving us the AIC values. Change of AIC value when you add age, when you add sleep hours, when you add work hours, when you add health score. How does the AIC value change? And then if you look at the summary, you can see the only significant model is this, just the substance use score by itself, the basic model, right? So none of the other things that we added are significant. So that's what it's saying. So the best fitting model is actually the basic model. So that means none of these things are the predictors of substance use score. So that's what it says. Okay, so but if you get a real world data set, so please try to repeat this process using a real world data set that you can find. If you work a little bit hard, you can actually find a data set by yourself and download it. Yeah, there's lots of data sets available that you can just freely download and then import them into R. So that's one example. I'm going to show you one example data set and how to do that. Okay. But after this process, I'll explain that. So this is actually forward selection. Similarly, we can also I have explained how to interpret. So yeah, forward selection adds predictors one by one based on their statistical significance to optimize the model fit. Okay. So this is the backward elimination. Okay. So in the backward elimination, we are first going to have the full model, and then when you give the full model, the this a step AIC function will actually eliminate one variable at a time, because we are telling the direction is backward. Earlier I forgot to tell you the direction is forward. You see, you have to clearly say what the direction is. So forgive me, I forgot to explain what these arguments are. So first you have to give the model, and then you have to give the direction. So the direction is forward in this case. And then the scope is actually the variables, the independent variables, set of independent variables that we have selected from our data. Otherwise, it will it will not be able to identify what independent variables are. Okay, so that's what the forward selection does. So this function, and then if you look at the backward selection, so this is what it does. Okay, so first we have to identify the full model, whereas in the forward selection, we had to identify the smallest model, right? So the basic model. And then we call the backward step function. Here we don't have to give the scope, because scope is already included in the full model, right? So all these variables that we considered are actually the independent variables, where I need to get rid of this gender, because it's a binary variable in our case. So so let's run this and see what it's doing. Okay. So you can see it is showing the results. First, it's running it for the full model, right? You can see the full model, right? It has everything, and then it's giving the AIC values by removing one by one, and then we remove. We have a model that has where you remove the health score, right? And when health score is removed, and then you just remove one at a time from that model, and then see what it does. Likewise, you can see all the fit values of the model, and then if you get the summary, it will show you what the best fitting model is. So that is also clearly saying it's only this basic model is the best fitting model in our case. Okay, so that's what you find. So this, so you see how easy it is to determine the best fitting model, right? So instead of like handling all these data by yourself, right? So adding this variable, that variable, is it going to work? Is this not going to work? So some researchers, when they learn these things, for the first time, they since they don't know these tools, they just struggle. Okay, so they spend hours and hours adding a variable, removing a variable. Or if is it going to increase the fit? Is it going to help with the hypothesis? So, but we have these processes that we can use. Okay, that could be helpful. So, I'm pretty sure that these things will be helpful when you do your own research. Okay, I think, let me see if there's anything. Yes, there's other mixed, like forward, backward mixed elimination. So which could be ideal when we have lots of variables, because we may have to add one and remove the other simultaneously. So where the fit is going to be better, right? So yeah. So we can compare the model fits using AIC, BIC values. So um, so the models with the lowest AIC, BIC value is considered the best fitting model with the lowest complexity. Okay. So if you run this, so you may be able to see that. So let's take a look at those numbers. Yeah, the step forward and step backward, if they all are giving all these AIC values, they're pretty close to each other because we've already found what the best fitting model is, right? So yeah, so that's what it's going to show you. Okay, I think this concludes the entire section of the linear regression. And
Dr.
Yes.
Should we go for a break before we start the new one?
Yes, we should. I was actually going to tell you. You just read my mind. So let's take a break because I also need one because we are going to yeah. So yes, so be prepared because we need to have a clear R environment, and I'll explain you how to download the data set. Now there's a small data set. It's not the best data set, but definitely if you spend little time, definitely you will be able to find a better data set. Okay, online that you can practice yourself. So before after ending this, the entire session, please don't keep things aside. Learn, practice, and just put everything in your head and learn all these things, these skills thoroughly, and then you can keep them aside. Otherwise, you will forget, because if you just by listening to this and copying and pasting these things, you might be able to do it by do it, like you might feel comfortable. Oh yeah, I can do this. But when you start doing things on your own, you will realize that, oh, it's not that easy, right? So that's you don't need that. But and also when you do things by yourself, you learn and you engage your brain better, so that then that will become your knowledge, right? Otherwise, this knowledge is going to have a peak during the course, and then after a few days, it will just be diluted. We don't need that. Okay. All right. So let's take a break. and then I'll be back in like 15 minutes. I'm going to mute myself. Can you please help me unmute in 15 minutes?
Yes.
Okay, thank you.
Thank you. So let's
Okay.
take a break, please.
Okay, so we are back. And so before I forget, let me talk a little bit. Let's go back to our previous section. I was planning to explain this later on, when we talk about some advanced methods. But I want to let you know that. So in this um, multiple linear regression and linear regression using this LM function, you can actually include binary data also, or like categorical data also. So definitely that's doable. So how categorical and binary variables are handled in LM function? So I'm actually talking about the LM function right here, right? So for example, let's say like here, I'm going to add, let's say, gender. So it is going to definitely binary variables.
Dr. Casula,
Yes.
you're not sharing your screen.
Oh, I'm so sorry.
No worries.
Yeah, I always forget. Thank you for reminding. Okay, so let me go back here. So you didn't see what I did. So we're looking at this model. Let's say this is our model. Okay, so let's forget about all these things. We are not talking about forward or backward stuff anymore. So here I want to explain how to incorporate these categorical variables that you cannot eliminate, because you may have maybe most of your data is categorical, right? So and maybe there's some continuous, right? So it really depends. So definitely you can include categorical data, and you can also test for those assumptions, but with some caveats. So you need to be careful with those. Okay, so you have to just run it, and then you will get the result. Definitely, you will see. So it's just going to be considered as the binary variables like 0 and 1, right? It's just going to um, um, uh, be included in the linear regression model that way, right? So this the LM function will treat these variables as numerical predictors. So where like one category serves as the baseline or reference group, and the coefficient for the binary variable represent the difference between the two groups. Okay, so by default, this function is developed that way. Okay, so you don't have to do any additional work. It is automatically going to be taken care of. But the biggest concern that you may have is how do I test for these assumptions, right? So that's the million-dollar question. So can you test the assumptions of multiple linear regression with categorical and binary predictors? Yes, you can test the assumptions of multiple linear regression even when your model includes categorical and binary variables. But the interpretation of some assumptions definitely change when these types of variables are involved. So uh, first thing, like if you talk about linearity, so the linearity assumption refers to the linear relationship between the predictors and the outcome variable, right? Remember? So, but for categorical variables, as we know, linearity does not apply in the same way, because these variables represent distinct groups rather than continuous relationships, right? So you cannot have some sort of a continuum, right, of observations, right? So when categorical variables are included, so you look for linearity between the continuous predictors and the outcome. Okay? For categorical variables, the model assumes different intercepts for different levels of the categorical variable. So which is not linear in the same sense as continuous variables. Okay. So definitely you can still test using residual plots to assess linearity, surely, but with categorical variables, except to see distinct horizontal bends corresponding to each category. So just be aware. So likewise, um, you can actually test for normality, homoscedasticity, and independence, and multicollinearity. So with the um, with these changes, okay, you just need to be aware of that variable itself. So when you see the plots, for example, in multicollinearity, so when categorical variables are included in your model, um, multicollinearity can occur if, for example, dummy variables created from the categorical predictors are highly correlated. So this can be problematic if the categories overlap in their representation. Okay, so you can research a little bit more about this and learn. So again, yes, definitely you can include them, but be cautious when we test for those assumptions. And how about the outcome variable? Can we have categorical variable here in the linear model? Anybody who was give it a try? Does anyone want to respond? Type here. The answer is no. The linear regression models, the relationship between predictors and a continuous outcome, by fitting this model, which is a line, that minimizes the sum of squared distances between the observed and the predicted values, right? So, so through this, in this approach, we assume that the outcome variable is continuous and normally distributed. So you can see those both of the assumptions will be violated if we have an outcome variable as a categorical variable, right? So that would be an issue. So so if you were to use a categorical or binary outcome, the linear model would produce predicted values that are also continuous, right? So these continuous predictions do not make sense for categorical or binary outcomes. So that would be problematic, right? So you cannot use them. So then what can we do? So when the outcome variable is binary or categorical, so we have other types of regression models so that we can use. For example, we can do logistic regression for binary outcomes, right? So there's lots of functions available in different libraries or packages where you can utilize them to perform a logistic regression. Okay, so for example, so we can use a GLM function. I can just type it. Let's say model logistic, and you can use GLM. Okay, so if you type GLM, it will show you, what you need to enter here. So first you have to enter the formula, right? You need to have your outcome variable, right? So this time the outcome variable, we need to have a binary variable. What is the binary variable? Gender, right? So it's gender. And then you need a predictor, right? You can see if, for example, I'm gonna, let's say this is substance use score, right? So that's the predictor. And maybe we can add something else. I'm just adding things randomly. Okay, so and then you have to define the family, right? So family is like, what kind of a distribution it is. So see, the description of the error distribution and the link function to be used for model. For GLM, this can be a character string naming a family function. A family function or the results of a call to a family function. For example, glm.feed. Only the third option is supported. So this gives the description. When you start typing, you will start seeing what you need to type there, right? So you can just type tab, and then you can use like binomial distribution. So yeah, and then you have to give the data also. So likewise, like I'm not going to run this because I didn't plan to do any of this analysis. And then the next argument is data. And then if you run it, it will give you the result. Okay. So that's one thing for binary variables. And then when it comes to the categorical variables, where you have more than two categories, you can use multinomial logistic regression. Okay, so these are also a little bit like advanced. So both of these models. So that is another reason that I did not include in this basic concepts. But I'm pretty sure you may have to use some of these models in your data, because you may not have all continuous variables, right? So libraries, there's lots of libraries that are available for multinomial logistic regression. So where if the outcome variable has more than two categories, right? So one library is, I think it's NNet. NNet is one library. Okay, so that is one library that you can use, and then that has let's say like no, and then you can use function multinom. Yes, right here, this function. And then you have to similarly you have to give the formula, and then you have to give the data, and then you can run the model and then get the results. So interpretation is different. And then so you may not be able to test for this assumption, linearity and all these things, but whatever the assumptions that we use here should be tested for. Okay, so but these assumptions that we define here are applicable only for continuous variables. Okay, so I'm not going to cover these topics, but I just want to let you know that these things are also there. So it's not that you have to have only continuous variables to run a linear regression model. Okay, so that's not the case. So there's other functions, other methods that we can use to analyze all kinds of data. Okay, all right. Yeah, so I think that is it. So let's clear everything. And let's get to this data set. So we have a data set here. So first we have to download it. So I have found that this archive, which is actually a really great archive for anyone. Okay, right here. So now, so this is a data set that includes, I think, 5,000 or something records, and it's giving the age, work class, and then the education, marital status, occupation, relationship, race, sex, and I don't know what this is, capital gain, capital loss, hours per week, and country, native country, and then income. So this is a data set that we are going to use. Okay, so you go to this. I can put that here, right here. So it's in the chat. So click on that link and then download the data set, and then you may have to cut it and paste it into your. First, what's the down? So the process is done. You go. Okay, let's go slow. Okay, I don't want to go fast. I'll give you a few minutes. So first, go ahead and download, and then when that is done, you have this this file. So you're going to cut, and then you're going to go to your works place, right? So where is your project works directory? So you have to go there. It's right here. So, and then you paste it there. And then you have to extract. Okay. So once that process is done, you have this file, right? So you don't have to open it. So adult.data. So that's the data file. So you cut it and come back to the directory and then just paste it here. Okay. So in my case, I already have pasted. I'm not going to do it again. So make sure this adult.data file is inside your directory, project directory. Okay. So right here, this file. Can maybe at least one of you say, okay, like when you're done, then I can proceed, because I don't want to rush through the process. I really want you to do this with me together.
If you guys are finished down uploading the data set, can you just give us a thumbs up, please? Thank you.
Okay, all right, good. Now, so now the data set is right here. So we need to go ahead and then import this into our R workspace, right? So let's go ahead and do that. Actually, before that, let's try to understand what the data set means. Let me try to go back there. So it's giving us some some information here, right? So we need to understand what variables are categorical, what variables are binary, what variables are continuous, like or integers. Um, so I'm just trying to see how to copy paste this, because you need to understand, what, because I don't have a kind of a data dictionary, but you should be able to come back to this and refer to that. Okay, so that's what um, um, that's what I want to tell you. Okay, let me see if I have the other file here. Just 1 second. Okay, all right, I found it. Okay, all right, so here here's the definition of all the variables. Okay, so you have age, age of the individual in years, and then the work class. Um, so usually the type of employment um, or the working environment. Okay, so it's giving this private self-employment, federal government, likewise. Okay, and then you also have the final weight. So which is representing the number of people in the population that the individual observation is supposed to represent based on the sampling process. Okay, so if you have one record, so that this weight represent how many people um, are being represented by that record. Okay, and then the highest level of education. So you can see that's given here, and then education number. So the numeric representation of education variable indicating the number of years of education completed. Okay. So yeah, so these you need to understand what these variables mean, right? So otherwise, you cannot do anything, right? So if it is, especially if this is a secondary data set, you need to first study, what these variables mean. That's what I know I was trying to explain. So let me share this with you file. I'm going to stop sharing because I don't want you to see everything on my screen. I have some of my research stuff. Okay, so I saved it, and so it should be in your chat. Sorry, I should have prepared this file. Okay, I totally forgot about it. It's right here. Okay, now you should have it. Okay, did you get it? Yeah, so so keep that on the side. Okay, good. So keep that in side of your screen. Perfect. So so that you can refer to that. All right. So let's start. Let me share first before I forget, because I always forget to share. And now let's try to import the data first. Okay. So number one, so we have a data set that we need to import. So we can just use the data. So if we assume the data is like comma separated, so which is actually the case. So if you can just like open the data set. If you go to the file directly, you may have it, right? So if you can see, if you open it, see it's comma separated, right? So since this file is comma separated, so you can just simply use CSV function. So that is available in our base code, right? So we can use that. That's also other data types that we can import. So for example, the data set that's being prepared in SPSS, SAS, when in other various forms can also be imported. So you can use like this, see right here, import data set from the file, and then in the menu you can see import data set. You can see from text, base, read R, and from Excel, SPSS, SAS, Stata, all these things can be done. Okay, so I'm not going to use them, but instead I'm just going to type my function. Okay, so let's say the data set is adult data. So I'm going to go a little slower so that you can follow. Okay, and then read. Yes, read.csv. That's the function that we use. Okay. So first we have to identify file, right? So the file, since the file is located within our project directory, we don't have to give the path, right? So I'm gonna give the file name, right? So it's adult dot data, right? And then it also has a header, right? So we have to say header is true, right? Sorry, I don't know if it has headers. So let's see. We can take a look at it. No, it does not have header. So header is false. Okay. So, false. And then we have to identify what the separating mechanism is. So you said sep, and then if you put like tab, if you hit tab, it will complete. You don't have to type everything. So this is going to be comma, right? It's since it's comma separated, right? And then if you want to also consider string as factors, so you can say true, or else you can say false. So depending on the type of data. So let's say like a string as factors. This should not be the case. If you have names, people's names as a string, you should not consider them as factors, right? So because then you can individually, like, each column, you can convert them as factors without just considering the entire data set as factors, right? So you don't need to do that. So that's why I'm going to say it's false. Okay. Okay. So if you run this, so it should import the data set into the environment. See, now it's there, right? So it has, if you click on it, so you can see there's 32,561 observations, and there's 15 variables, right? And we can clearly see the variable names are not given. So it's just saying V1, V2, V3, V4, V5. So this is how, a typical data set looks like. In some cases, if you're fortunate enough, you may also see, the headers and proper definitions of variables. It really depends on, how the data, collection team created this file, right? So, but in this case, you have to definitely rename. So these column names do not make any sense to us, right? So that should be actually our first task, right? So so let's try to see, you can look at the entire data set like this, or if you use that head function, you can just see the first few columns of the data set. Okay, so it will show you all the variables. Are we good? Are we making progress? Were you able to do, import the data set? Yes, okay, perfect. All right, and then, so we are going to use the function column names in our base package to rename the columns, okay? So when you rename the columns, make sure they're meaningful for you. So you can use the text file that I gave you where you have the data dictionary. So identify the names, a good name. You don't have to use the same name that they used, because it may not be the best name in your domain, right? So whatever there's different jargon terminologies that you use in your domain, right? So make sure you use the appropriate domain for your research. Then that would be easier. Obviously, these column names may or may not be included in your plots or results, because when you go to your data results section, and then in this kind of discussion section, you will not include these variables. You can have, if you have meaningful variable names, then you can definitely use them. So otherwise, you may have to be more descriptive of each variable so that people would understand what you're talking about, right? So otherwise, you never use the original data set name, the variable names in your results if if they're not really self-explanatory. So we'll use this function column names, and the data set we have to give the data set adult data. And then we just have to give the names, right? So that's all you have to do. So and then it will identify the name. So now we have 15 variables. So the first variable, if you look at our data set, first variable is age, right? So go back to the text file and confirm that. Okay, so I want you to really do this by yourself. Don't just type what I type here. So that's the first variable. And then the second variable is, again, you can give, whatever the name that you want to give it. Okay. I would not keep space between the words. When you plot, then it might be a little bit of an issue when you do plotting. So you can always rename. Okay, so it's better to keep variable names without any space. You can use like underscore. Like for example, here the next one is work class, right? So I'm going to say it's like work underscore class. Okay. And then the third variable is the weight, right? So it's final weight. So I'm just gonna elaborate that a little bit. I don't like this FNLWGT. I'm just actually gonna expand it. Final weight. And the next column is education. Right? And then let's go to the next column. That's education number, right? Yeah, that's education number. So let's say it's education number. That's like number of years, right? You can again, you don't have to do what I'm doing here. Okay, you can give your own name. That's more meaningful for you. And then what's the next one? Marital status, right? So marital status. Okay. And what's the next one? Occupation, right? So you can also say just like job or something, however you want to call it. Okay. Occupation. What's the next one? Relationship, right? The next one is race. And then the next one is gender. So this capital gain and capital loss. So you can see the definitions and understand what they mean by those like gain and losses. Capital gain, and then capital loss. So you may not use all these variables, right? So you can get a subset of variables, but not at this point. Okay, once the data cleaning is done, you can subset. Right now, you have to keep your entire data set like this because when you do the imputation, you have to make sure you have the entire data set. Otherwise, you may find you may find it difficult to understand the missingness pattern characteristics, and then what is causing the missingness, and also the imputation process. So it's always advisable to have the entire data set for those reasons. Okay, and then capital loss, and then hours per week, right? Hours per week, and then native country. And then finally, the income. Okay, so this should rename. So if you run this, um, let me open the data set. So right now, as we can see, these column names are not meaningful, but if you rename them, you probably would be able to see the new column names are being applied. So now everything is clear now. So we can see they are meaningful, right? So yeah, so this is the data set, and you may see like there's some missingness, right? So you can see these question marks are indications of missingness, so they don't have values. So we have to take care of that also, right? So, but before that, let's make sure, like, if this, renaming was successful, right? How do we check that? Is there a way to test it? Yeah, if you put head and then data, so you should be able to see what it says, right? So you can just look at the data. I looked at it right here, or else you can do this head command, right? Like this. So it will show you the variable names properly added and modified them. Okay. So now we manually convert the categorical variables to factors and then numerical variables to the appropriate types, right? So either they're like integers or numeric, however you want to have them. Okay, so that's the next step. So we can do this one by one. So for each column, we can manually do this, or else we can write a function to do this. So for example, if you go into work class, so now it's being considered as a character, right? But we need this to be a factor, right? So we need to change that conversion. So first thing is like, we just type, adult data, and then you use the $sign. And then when you use the $sign, it will show, all the variables that you have in your data set. And then you start typing, the name of the variable, then it will show you like work class. And then you can either like, hit tab, or you can just click on it, right? So right now it's a character. I'm going to assign this as a factor. So we just use as factor function with the argument, again with the same column name. Okay, adult data set work class. So this should convert the first, the work class column into a factor variable. Okay, so if you go back here, now you can see factor with 9 levels, right? So it's properly being identified. It actually has 9 different levels, which worked really well. Okay, and similarly, so if you go to education, so this is also a factor because we have different, responses that people gave, right? Bachelor's degree, high school, diploma, 11th grade, master's, 9th grade. So these are like, different categories. So basically, these categorical, variables should be considered as factors. So we do the same thing. So adult data, and then education. As factor, and then education. Okay. So I'll let you figure the other things out. So let's move on. So to the next ones. Make sure you understand what you're doing. Okay. Assume that you have no guidance coming from me. So and see what you have to do with the other variables, right? So age is there, right? So age should be an integer, right? So now it's showing it as numeric. So I think it's better to consider age as an integer because we don't have like how old are you? I'm like 39.5 years old. Nobody says that, right? So it's all like whole numbers. So I think it's better to do that conversion also. Okay, so likewise, why don't you go ahead and convert this data, because each and every variable should be properly identified, um, and then only the computer knows, what this variable type is. Okay. So don't look at what I'm doing, do things by yourself. Okay, just try to figure it out, and then try to do the conversion. Okay. So basically, any categorical variable, right? I mean, these are the questions that you ask people, right? So, so out of these, like, 7, 8 different categories, like for example, education, right? So there are 16 education levels. So someone has to select, one out of those 16, right? So definitely it's a categorical variable. So same goes to marital status. So there's 7 levels, right? Are you married, and divorced, and this, yeah, you can have like 20 different things, for these marital categories, because there's lots of different types of status available. So likewise, you need to identify them. Okay. I'm referring to my text document. Okay, make sure you read that and then do this meaningfully. So I have done all these. I have class, education, mental status, occupation, relationship, race, and then we also have gender, right? Gender, that's going to be categorical, so that should be a factor. And then native country, and then income. It's also in categories, you see. So income could actually be a continuous variable if you ask people to enter their income, right, directly here. But instead, they ask, like, what's your income category? Like, is it below 50,000 or between 50,000 and 75,000? Likewise, so it becomes a categorical variable, right? So that's how income became categorical. So that then that should also be a factor. Okay, so I have identified all the categorical variables and then converted them into factors. So it should be good now. So next thing is if you look at age, so age, since it's an integer, so we need to identify it as an integer, okay? So start data age. Then, so education number, right? So that, what is that? So number of years, right? So then that also becomes an integer, right? So we don't have decimals there, right? So we do the same for education level. Sorry, education number, and make them an integer. Okay, and then what else? Final weight. What is it? So weight typically could be a decimal. So I don't know if we have any decimals here, but it's better to keep it as decimals. I mean, when you consider it as numeric, so it can also have whole numbers, right? So that is the case. So you should be okay. Final weight. So it's going to be as numeric. Okay. Okay, and then capital gain. So capital gain, I don't know what it is. So yeah, it's safe to keep it as numeric because we may have some um, uh, decimal numbers there. So and then you do the same thing for capital loss also. And then lastly, the number of hours per week. So where is it? Right here. So that is going to be an integer. By looking at the data, you can identify if they're like, really integers or, um, they have decimals, okay? So okay, all right. So yeah, so that's all done. So I'm going to run this also. So how are you doing? Are you following me? Are you getting there? Okay, a bit confusing, but okay, all right. So keep going. So yeah, so you might feel it overwhelming, but if you observe the data closely, you may recognize. Usually, along with the data, they also give you like the original survey that they used to collect the data, right? So that question can clarify things even further. So in our case, we don't have that. So in your case, like it's most likely it's going to be like, even easier, because if you have secondary data, they usually give you, the questionnaire, right? So that they use, how they ask the questions. So that might clarify most of these things, especially like numbers. You have to identify them properly. Otherwise, it could be problematic, for all the um, the following steps. Okay. Right, I'll give you a couple of minutes. I mean, we don't have to rush this process. I mean, the most important part is actually this, like, it's not about coming here, like, and sitting and listening and then, oh yeah, it's good. I know how to do R, programming now. It's not that. This is what's important. Okay, so I would not rush this, and we'll take for a few more minutes, and then. We can see. We can also do this using loops, but at this point, I'm not gonna introduce that to you because it's a little complicated, and you don't need to do those advanced loops and everything. Okay, at this stage, if you can handle it this way, that's more than enough because you just get the job done. It doesn't matter if you type like 100 lines of code. It's gonna be okay. So yeah, you don't have to uh, do like all fancy things like adding loops and conditions. Yeah, so you can write like a function to do this and automate it. For example, like if you have like 100 variables, right? So you have to like do this 100 times, right? And then you also have to look at the data and identify, if they're really, categorical, or if they're really integers, or if they're really like, decimals there. So manually, like, doing this could be really painstaking. If you have a really large data set, like hundreds of records, right? So in that case, so definitely you can automate using a function. You have to write your own function to identify, what type of data it contains, and according to that, we just do these operations. Okay, that's also possible. So, but that is not necessary at this level, and you don't need to know how to do that. Still, you can get your work done, and you can get your publication or whatever you want to do without having that advanced, like, knowledge. Um, so yeah, it takes little time, but still you will get there. Okay, so can we proceed? Okay, good.
Seeing
Oh,
yes.
okay, good. All right. So now once the conversion is done, you can use, str function to verify, the data types. So str, and then you just type your data set name. So then it should show you, what type of clearly reflected here. So any change, all changes that we made are here now. It's good. So we are good to go now. Um, and um, and then we can go to the next step. So the next step is actually, so now we have to clean the data, right? So if there's any missing values, we have to take care of them, right? So, so how do we handle missing values? Um, so So obviously, like, if there are like missing values for example, let's say like names. I mean, you cannot replace names with something else, right? So that's not going to be useful. And in your analysis, you don't really like, need to deal with people's names, right? Unless you like, do any qualitative, data analysis. So you may need that kind of approach. But in statistics, you don't need to work with strings mainly because you cannot analyze, data if it's in the string format and it's not meaningful. So, but anything else, if age is missing, so we need to assign, let's say like the median age, right? You can say median age, right? If age is missing, just assign the median age for that missing value. Okay, so let's do that. Likewise, you can do that for all the variables, however you want to do, right? So usually, I'm going to just use median. I mean, you can do median imputation, mean imputation. I explain all those things to you. It's up to you, but right here for this demonstration purpose, I'm just going to use the median. Okay, so you type adult data. Let's impute age first. So we are going to test, if it is null, right? Only if it is null, then you have to do this. So is.na is a great function that we can use to test if it has null or empty content. Okay, so we check if it's empty, and in that case, whenever we have an empty value, so that is going to be replaced with median. Okay, so that's what we are going to do. Adult data, age column, and see within that age column if there's anything that is null. So this is.na function is going to identify that, and then you go to the assigning process where each and every missing value is going to be replaced with the median of that column. Okay, so adult data, find the median of that column. This is how you find it, age. And then you also say na dot remove equals true. So this should, I don't know if we have any missing values. So if there's any missing values, so it will be replaced. So there may be some missing values. So they will be replaced. Okay, because we have like 32,000 records. I cannot look at it, but obviously you can find, right? So we have functions to check if there's any missing values, but let's do it anyway, right? Because we are in the process of learning, right? So that's done, we imputed that. Similarly, you can repeat this process for, let's say, I'm just going to copy paste, okay? So because that's easy. What's the next column? Weight, yes, let's do it for weight, right? And remember that we cannot use the median value of age to impute data in final weight, right? So it should be, the median value of that corresponding column, right? So otherwise it's not really meaningful. Okay, so that's done. And then let's do it for what is the next one? Education, number of years, right? So let's impute that also. There we go. Okay, so that is done. And then the next one is capital gain, right? So I'm pretty sure there's missing values there. So let's impute that also. Okay. And that, and then do the same for capital loss, right? So okay. So what else? Do we have anything else that needs to be imputed? So median imputation is we only do that for like integer variables, right? So, or numerical variables that can be done, right? But if you have categorical data, so you have to use another way, right? So so we will discuss that, how to do that. But we also have hours per week, right? So there we go. Yeah, we need to do that also. It's always nice to have comments, okay? Something that I did not do because I wanted to save time, but put some comments so that you know what you did, right? So for example, so you can, just type here, imputing variables, okay? So something like that. And then you can like, type whatever the variable, I mean, renaming columns, and then here converting the variable types. Likewise, it's better to have these things. When you come back, you would know what you did, right? So it's better to have those records. So yes, everything is imputed. All the numerical variables are imputed. But now we need to impute categorical variables because I'm pretty sure there are missing values. For example, we are looking at occupation, right? So we can see right here it's missing, right? So, and the work class is also missing for this individual. So we need to take care of that. So in order to do that, so we have to, we don't have a function to determine mode, like median. So we have to write our own function to do that. So why don't we do that tomorrow, and then we'll proceed with the analysis. It looks like we had enough for the day, and you must be tired, and so am I. Let's call it a day. Then meet tomorrow, and then we can finish this. And then the following day, next day, next week, we have another day. We can do some predictions.
Okay. Thank you so much, Dr. Kusgola. So just for clarification, and when we make the announcement and send materials, we'll tell them that tomorrow, this is the data set that we'll be using. We'll be continuing where we left off. So we'll make sure that everyone received that instruction as well as a copy of some of the syntax. Okay.
All right.
Thank you
So,
so much.
yeah. All right. And then I'll see you tomorrow.
Okay. Have a good day, everyone. We'll
Okay,
see you
bye.
again tomorrow. Goodbye.